So yeah, good morning, everyone. Thanks for the introduction. Hopefully everyone can see it. Yeah, so today I'll be talking about Qiskit, which is an open source coding software in Python that lets you program and control real quantum computers. It was created by IBM, and originally it only had access to IBM's quantum computers, but as its popularity has sort of increased, other quantum computer companies like IonQ are beginning to make it compatible with their machines. And in the image on the left is what IBM's quantum computer looks like. So before we get into the substance of the presentation, I'm just going to go over sort of a structure and also some goals. So first, I'm going to start by going through some conventional PowerPoint slides to explain the background behind quantum computing's power and some fundamental concepts. And that should be relatively quick, and I'll just introduce Qiskit briefly. And the goal of this is just to get you familiarized. I'm sure, based on the previous presentations, you're already relatively familiar with it, but just to sort of go over that. Then I'm going to switch over to show you how you would actually go about accessing Qiskit for yourselves online, and I'll give like a live demo of Qiskit's interface and features. And the goal of this is just to show sort of how easy it is to start programming a quantum computer in your own home. And you can think of it as a sort of live tutorial for how Qiskit works. And so one main point that I want everyone to take away from this is that it's really easy to get started with Qiskit. Even if you have no prior experience with quantum computing, or even if you have no prior experience with coding at all. When I first started, I did not have that much knowledge about quantum computing in general, but Qiskit, along with the tutorials it provides, it also has comes with a free textbook. It makes it really easy to learn. And so, I definitely encourage you should take you to take that kind of as a big point. So also, if at any point you have questions, please just unmute and ask them. And you can also put them in the chat. I actually just saw the chat. But okay, yeah, so yeah, no questions yet, but yeah, just put them in the chat and I'll try to address them once I'm done screen sharing. So with that, we can kind of start the actual presentation. So just, some background. So a classical bit, 0 or 1, most of you are probably already familiar, but then a quantum bit is a superposition of 0 and 1. And so the figure on the right is just kind of shows the distinction. Classical bits only have option of 0 or 1, but quantum bits, can be a superposition and have multiple. So this is the primary way that quantum computers are able to achieve exponential speedups and other major advantages over classical computers. And it's because of that superposition that you're able to sort of store more information. I'm going to check the chat just to, okay, yeah, so that's, okay. Yeah, so just to give an example, and you're already probably familiar with it, but if you have an initial quantum state in the 0 state, you apply a Hadamard gate, then it turns it into a superposition of 50% chance it's in the 0 state, 50% chance it's in the 1 state, and that's just sort of to illustrate what you can do. And that's the general schema for quantum circuits. Is you have a number of qubit inputs, and then you have some number of quantum gates that do various transformations to the qubits, and then you're left with a final state which you can measure. Yeah. So how does Qiskit fit into this? Basically, on the right, you see an image of a quantum circuit. Qiskit can basically encode those quantum circuits, and then you can run them on real quantum machines. And so basically, that's its primary use. But I do want to emphasize also that Qiskit provides many other resources, such as I mentioned before, a free textbook for users, as well as tutorials. They have a YouTube channel with tons of explanational videos. They have example circuits and experiments, and also free optimization software built in to make sure that your circuits are working as well as they can. And so with that, that was pretty quick, but I'm just going to stop screen sharing and just switch to my Chrome browser to show you kind of how you would access Qiskit for yourself. So we should be seeing it now. So yeah, the basic way you would start is you would go to your Google Chrome browser. You would look up Qiskit. You would pull up qiskit.org, and then you're going to be brought to this screen where, initially what it'll start with is just, it'll kind of highlight, exactly what Qiskit can do. So, again, it provides access to quantum circuits, as well as, being able to execute those quantum circuits on real quantum machines. And then in addition, it has a bunch of quantum algorithms stored, and it explains them. And so, you can look at a bunch of applications. And so in this, they highlight optimization. There's chemistry applications, and you can also use those stored quantum algorithms in your own quantum circuits. They also have noise mitigation, which is important because qubits in quantum computers have lots of error. because they are sensitive systems, and even small interactions with the outside environment can make the circuit execute in sort of weird ways. So Qiskit provides ways to sort of reduce and also study the impact of noise on the quantum computer, but also ways to sort of optimize your circuits so that they're running smoothly. So the next part is where you would actually start being able to use Qiskit. So there's two primary ways to get access and start using Qiskit. The first way is to download the software. So it's based in Python, so you'll need an environment that can run and write Python. And so in this case, they recommend Anaconda, and it's a pretty good environment to use. The second way is by, and this is also the way that we'll be exploring today, is by using IBM's Quantum Lab, which is basically, it's on their web browser, and it's basically gives you everything you need, but you don't have to download anything. And it also has some more features that you might not have access to with the Python download version. So, this is a good way to start out if you're unfamiliar with, how things work. And so you'll need to create an account with IBM, but it's free. There is a paid version that gives you access to more of IBM's quantum computers, and they also have more qubits. But if you're just starting out, the free version sort of gives you everything that you would need. So if you just click on IBM Quantum Lab, it'll take you to this. It'll take you to the IBM Quantum Lab, but what we're going to go to first is the dashboard, which is sort of the home page of Qiskit. And so just kind of waiting for it to load. So the first thing you'll see is it provides some information about the kinds of quantum services that it provides. So in this case, your systems, there's 8 of them. It's referring to the actual quantum machines that you have access to. There's 5 simulators. So what that means is, like, they're not actual quantum machines, but they simulate what you would get with a quantum machine. And so the utility of this is that there's no error. So if you wanted to try out a circuit, you could get exactly what you're expecting to get. And so you can get more information by clicking View All, but you can also, and I'll show this shortly, but if you click on the dashboard and go to the quantum services, you can click that, and then you'll get this new page that provides more complete information about each quantum system. So, it shows the name of each system, shows whether it's online or not. It also provides the number of qubits that it has access to, as well as the quantum volume. And so what quantum volume is, if you're not familiar with it, it's basically a universal metric to compare quantum computers that, even if 2 companies develop quantum computers differently, quantum volume is a way that you could measure which one is, has better capabilities and lower error rates. And so, if you wanted to see more information about, IBM Q Santiago, you could click on it. It tells you how many pending jobs are on it. So that what that means is basically how many people have requested to use and run a circuit on it. And so if you wanted to use that quantum computer, you would have to get in a queue, and you would be kind of, 1398 in this case. But it also provides information about the qubit connections. So this is useful for optimization, where you want to basically choose the qubits for 2 qubit gates that are connected to each other. And so it provides not only how they're connected, but it also provides the degree to which they're connected. And it also provides the error rate for certain gates. So in this case, it provides the error rate for C0s. And that's the typical one that they'll provide, because that's the sort of a key gate. And so, you can use this information to further optimize your gates, because if you wanted to, make sure that your circuit was less complex, you would want to choose the qubits that are connected to each other for 2 qubit gates. And so that's sort of the information you can get from that. Below, it also has the simulators. Something you'll notice is that the simulators have many more qubits than the real machines. And this is just because they're not subject to the physical constraints that actual quantum machines have. And so, if you're just starting out, the simulator is going to be a great option, because the queue is usually pretty short, and it's got access to as many qubits as you could possibly need. So sort of going back to the dashboard, it also shows your API token, and this is what is going to be, you're going to use that token to basically get access to IBM's quantum systems, and that's how you would actually, that's how it authorizes you to use them. It also shows you your pending jobs as well as your completed jobs. And it has, kind of updates about Qiskit and other IBM quantum related news on the right. And then, real quick, I just want to highlight that they have special access programs. So There's a researcher's program which you can apply for, which you just have to submit your paper as well as the institution that you work for. And it basically, there's some benefits. It gives you a better queue. It also gives you better access to more quantum systems. And that would be free. You wouldn't have to pay for that because you would apply as a researcher. It also has an educator's program for teachers or professors looking to teach a class. And so, you would just provide the course name as well as a plan. And so those are definitely options that you should explore if you're interested in that. Other things on the dashboard, again, the quantum services is the page I just showed that has the sort of readout and information of all the quantum systems you have access to. There's also a jobs page where it shows basically all the jobs that you've run. So whether it be on a simulator or an actual device, it shows what time it was run. It shows the sort of name of the experiment. In this case, none of these are named. It also shows whether it's like status completed or whether it's like pending. And so pending is just, it hasn't been run by the actual machine yet. And then there's also a notifications bar, which basically just gives you sort of more kind of recent news about Qiskit. The user guides is going to be a really helpful section where you can basically, it's tailored for each person. If you're completely new, you can click on that link and then it'll take you basically to show you exactly how to use the quantum composer, which I'll do shortly. If you're a developer, educator, researcher, it also has a Qiskit Slack and also a Stack Exchange where you can, if you have any questions or you're not sure about something, you can always ask people and the experts will try and get back to you. So this is basically the place you're going to want to go if you have any questions or you want to explore something more. So going back to the dashboard now, we're going to start actually showing how to make quantum circuits and run them. So there's two ways to do this. There's the quantum composer, which is for, it's basically a graphical representation of circuits. And so you can drag and drop gates and it's a very simple interface. And it's very user friendly and it's for the people who maybe aren't familiar with coding. But, basically, so even if you don't know Python or, any sort of coding stuff, you can still do this and still start, making quantum circuits the day of. The other mechanism is the quantum lab, which is where you'll be coding in Python using Jupyter Notebook. And so that's for if you're familiar with, how to code in Python, you can do that. And that's also a good way. So we'll start with the circuit composer. So you just click launch circuit composer and it's also in the dashboard right here at the top. And so quantum composer and then quantum lab. And so what you're initially presented with is on the left, you have all of your circuits that you've created. You can create a new file and that basically just clears it out, creates a new circuit. And so the thing at the center is going to be where the actual circuit diagram where you'll make your circuit. So, on the left, you have your qubits. You also have a classical bit where you're going to measure. And so just to illustrate, you would drag a Hadamard gate. And then below you have these state vector graphs as well as probability graphs, and they would update to show the effect of the Hadamard on the quantum system. And, there's a bunch of gates that you have access to, not just the Hadamard gate. And what you can do is if you're ever not sure of what a gate means or you're interested in trying something out, you can always go to this operations glossary, which basically provides a full list of an explanation of every gate / operation they have. So like you'll notice they have classical gates, phase gates, and then these are not gates, but they're like specified operations that you can do. And so if you're interested in one of them, like let's say, we don't know what the if statement does, you just click on it. It'll show you what the symbolic thing is. It'll provide an explanation for it. And then it'll also show how it would be represented in Opencastle, which is sort of another coding thing that Qiskit uses, but we won't really focus on that. But this is basically the area you would want to go to if you're not sure what a gate does. You can also name your circuit, and then at the top, there's all the kind of conventional file edit, saving your circuits, etc. At the bottom, you'll have a state vector graph, which shows the coefficients of each state. And so in this case, the Hadamard gate is the only one applied. So what we're expecting is a 1/√2 coefficient for each of these states. And that's what we see. And then it also provides the probability. And so, 50% chance it's in, this state, 50% chance it's in the 0 state or the other state. And then it also, if you scroll to the left, my screen's kind of small, but if you had a bigger screen, you would be able to see everything kind of there. But you would be able to see a block sphere representation. So here it is. And so this is just another way of visualizing it. And so, you can basically see exactly what is going on in your circuit, real time. And then if you want to actually run this circuit, what you would do is first, you do need to add a measurement. And so you would add a measurement to whatever qubit you're interested in. You would click setup and run. You would choose, you could scroll down, you would choose which quantum machine you want to run it on, and then you would click that one, and you would choose the shot count. And what the shot count is basically how many times the experiment is run. So typically 1024 is the default, but if it was just one shot count, then the thing would measure either as 0 or 1, or either one state or the other state, and that would be a bad kind of result, because you're really looking to see that they're in a superposition, that there's it's equal chance that it's in the one state or the other state, and so that's why you have more shots, and so less shots, you fall prey to the error of quantum computing, etc. And so you choose the machine that you want to run it on, and so there's the actual machines that you could run it on, but there's also simulators that you could run it on, and then you would just click run, and so it's loading, and then there's this job button on the side, and so you would go there. And so in this case, I chose a real quantum machine, so the queue is probably going to be a decent amount of time, so it's going to be pending for a while. But what you can do is you can click on that, and it'll just show you kind of what step in the process it's at. And so, at this point, it's in the queue. But just to show you an example of what you could expect, if you clicked on the jobs page, it should also show up there, and indeed it does. But just to show kind of something you could expect from a completed job, if you clicked on it, what you would get is, completion time. And so in this case, yeah, it took 34 minutes, which is kind of long, but it shows the number of shots, all the information, the time it took for it to transpile, validate, and then it'll show you the actual, the shot count for each state. So this is kind of what we were expecting, 50%. It's not exactly 50%, just because the shot count isn't so large that you can get exactly the half the number of shots in one state, half the number of shots in the other state, but it gives a good representation. And then it also provides a diagram of the circuit that you made. And so that's kind of what you can expect from when you click on the job. And then if we go back to Quantum Composer, something else you can do is, if you wanted to see what your circuit that you've created looks like in Python, you can just click this button. And so right now it's in Opencastle, which is another way of representing the circuit. But I'm focusing more so on the Qiskit Python area. And so if you click that, what you have is basically what it would look like in code form. And so, let's say you wanted to create a circuit in Quantum Composer because it's faster that way. And then you can just copy paste this code and then put it into a Python thing, and you would be able to run it, and you would get the exact circuit you were interested in. And so that's a useful aspect. So that at this point, I've kind of showed exactly how you would set it up. So, this is obviously a simpler circuit, but you could, obviously, just apply a bunch of gates in, the ways that you want it to. You can also add qubits. It depends on how many qubits the simulator has access to, but, I added a third one. You can add, a fourth one, etc. And the only limit is really the simulator or the computer that you choose to run it on, and whether or not it has that number of qubits. So at this point, I'm going to go to the Quantum Lab, which is the place where you would actually code in Python and Jupyter Notebook. And so if you click on that, it'll bring up a similar page where you have on the left all of your sort of notebooks or your code, the different files that you've made. And so in this case, we'll be looking at a tutorial one that I made. And so, at the top, you have kind of the classic file edit. You can run your code. And this first thing, this first block of code is included in every, it's included in every like file. And it basically just, sets up the things you need to actually access the quantum computers, as well as access the software that Qiskit has. And so it's default, you don't have to worry about it. So it uses Jupyter Notebook. So one thing you have to be cautious of is you have to run everything sequentially. So if I were to, this circuit is defined in this block. And so if I don't run this block like this, then So in this case, I have run the block, and so this will work fine. But actually, I think there will be oh no, so yeah, so it works. But if I didn't run this block, then this wouldn't have been defined, and so it would have given me an error. So you do have to be mindful of that, and you do have to run it sequentially. But so just to give an example, so you would run, so the way you would define a circuit is like so, you have, whatever you want to name it, and then quantum circuit, and then the two parentheses values are, the first entry is the number of qubits that you're going to have access to, and then the second entry is the number of classical bits that the qubits are going to be mapped to. And so what that means is basically, even though the qubit can be in a superposition, ultimately when you measure the qubit, you're going to get a classical bit, a 0 or 1. And so that's what the classical bits are there for. And so if you run that, then the next step is, you've created your circuit, and now you need to add gates. And so the way, in this case, it's adding a Hadamard gate, and the symbol representation of the Hadamard gate is just a lowercase h. And then the first entry in the parentheses is a 0, and that's the qubit that you're applying the Hadamard on. And one thing to note is that the way it indexes qubits is 0 and up, as opposed to qubit 1 being the number 1. Its qubit 1 is 0, and then qubit 2 would be 1, and that's how they do that. And so you apply a Hadamard gate just by doing .h0, and then you apply a C0 gate, and in this case the symbol for that is CX, because the X gate is the not, or the X is the not gate, and so the controlled not gate would just be CX. The first entry is going to be the control qubit, and then the second entry is the target qubit, and so that's what you can expect. And then you apply another C0 gate, and then if you run this function called draw, and it's draw, basically there's other ways to represent it, but in this case I'm using MPL, and it'll draw it like this. You can also draw it in a different way that looks a little bit weird. Oh, and so interestingly, so yeah, so the circuit was recognized, but because this first thing wasn't run, the circuit gates don't show up. So if we run this, then we should be able to see the actual gates show up. And so indeed, so the Hadamard, the C0, and the C0 show up, but before they didn't, because this block of code was not run. And so all it knew was that a quantum circuit had been created, but it didn't know that gates were there. And so once you run that, you can kind of get a visual representation similar to what you saw in the quantum composer. And then the next part is basically running your quantum circuit. So in this case, we're going to use a simulator, but the process for running an actual quantum computer is you basically just take the name of that quantum computer, and then you replace it so instead of state vector simulator, you would choose IBM Q Santiago or something along those lines. And so you would get the backend. And so that's kind of the method for doing that. And you would define the backend, which is basically the system you'll be running it on. And so the way you would get sort of results is you would define job, you would execute. The first entry is going to be the circuit that you're interested in running. The second entry is going to be the actual system that you want to run it on. And then you get a result you use the result method. And then the output, you can get various things from the result. So you can get the state vector. And so in this case, it gets the state vector for this circuit. And then you can define how many decimals you want it to. And then, in this case, we've printed it out, but it provides basically, these are the coefficients for all of the possible states. And so it's, provides basically 8 entries, because it's a 3-qubit system. And so 2 to the 3 is 8. And so you get all of the coefficients. And so that provides the state vector. Another thing you can do is you can show sort of the actual unitary matrix that would represent the circuit. And so that is what is shown here. And so that's just a different way to sort of understand it. And so if you're interested in that, you can do that. Another interesting thing is there's things called barriers, which basically, in this case, the way you would add it is you just, dot barrier, and then the entry is an array, and it basically goes across all 3. So in this case, I've defined the range 3, and so it'll serve as a barrier here. And what it does is when you actually run the quantum circuit, IBM will automatically try and optimize it and sort of transpile it in a way that's efficient. But if you provide this barrier here, anything that's after the barrier will be transpiled separately, and it won't be put together or combined with the stuff before the barrier. And so that's something that's useful if you're, really trying to find better ways to optimize. And another interesting thing you can do is, in this case, I've actually created a new quantum circuit that is defined similarly as the one above. But it has, a barrier in addition. What we can do is you can add circuits. So in this case, you have a new circuit QC, and it equals the first circuit plus the new circuit, and it just appends them. And so, you would have the original circuit and then the barrier added on, and then there's the draw function again, and so you can see it. The next thing you can do is you can get the count number. So in this case, you use the execute method, you define the number of shots, and then you can basically get the counts basically. So, you can figure out, okay, so there were 534 counts in the 0, 0 state. So that means that, 534 times the experiment run, it was in this state, and then 490 times it was in this state. And then you can also plot that in a histogram using the plot histogram method. And so, there are other ways to, you can also, represent it in the QSphere area, but that kind of wraps up how you would actually go about coding in Python the quantum circuits. And so just real quick before time runs out, this is shown kind of the basic way you would approach, you would create a circuit, and then you could apply whatever gates you're interested in, and then you would kind of measure them and run your circuit using this execute method, and you would define your backend. But just to show sort of other things that Qiskit has, so I mentioned before that it has a textbook, and so you can click, you go to the dashboard, you go to this thing called Lab Docs and Tutorials. It has this Qiskit textbook link, and then it basically just has a slew of resources. Initially it starts out with the basics. The prerequisites part shows, how to set up your environment. It goes over Python and Jupyter notebooks. The chapter 1 starts with kind of basic qubits, just single qubit gates, etc. And, shows you Qiskit examples as well. The second chapter shows you more complex things. The third chapter gets into various algorithms, and it not only provides like a math explanation of them. If we just click on one, it provides the sort of introduction to the problem itself. It provides the algorithm, but it also provides a Qiskit example and a gone out like solution to that. So yeah, it provides a worked example, and then it also shows how you would actually do that in Qiskit. And it does that for a bunch of algorithms. Chapter 4 goes through like actual applications. So it goes through, in this case, it's going over solving systems of linear equations, but there's a bunch of other applications you can do. Chapter 5 goes over quantum error and ways to test and, mitigate error. And then chapter 6 goes over how to like basically investigating the actual microwave pulses that go into creating the gates. And so that's like sort of the next level of control. So I just wanted to highlight this because it just kind of goes to show that Qiskit has a lot of resources you have access to, not just sort of creating, quantum circuits that you're interested in. And so even if you're a complete beginner, it provides everything you could possibly need for what you're interested in. And so I think at that, I've kind of run out of time, so I don't want to take too much more time because I know there's another presentation, but I'm happy to take questions.
Thank you, Ian. That's great. I think we have